We're going to use our, you could use your graphing calculator to graph 2 to the x, the 2 to the x function, or you probably are pretty familiar with the behavior of 2 to the x. It's growing exponentially by powers of 2. So we could graph that one without our graphing calculator, but the reason why the graphing calculator is nice is to actually graph the derivative. Okay, talking about the function itself, the domain of the function, x is an element of the real numbers. The range, y is greater than 0. Remember, there's a horizontal asymptote at y equals 0. F of x equals 2 to the x is always increasing. So we can just say it's increasing for all real numbers. It is never decreasing. Okay, and the concavity of the graph, f of x equals 2 to the x, is always concave up on its domain. Okay, so using a graphing calculator that will graph a derivative, the derivative of 2 to the x looks a lot like 2 to the x, except it's a little bit shorter, right? The y values are below, and I'm just kind of roughing this in here. I have not plotted any actual points, but here are the y values in this table for the derivative values. Okay, so it appears that the derivative looks, again, a lot like 2 to the x, but it's a little bit shorter. Okay? All right. What is the domain of the derivative graph? Okay. Here on this slide, I have it in red. The domain of the derivative graph, again, is all real numbers. And the range is still y greater than 0. That's for f prime of x. Okay, again, this function is always increasing, so it's increasing on its domain. It is never decreasing. Its concavity is concave up. All right, what are the y-intercepts of each? So we know that the y-intercept of 2 to the x, y-intercept is 1. 2 to the 0 is 1. The y-intercept for the derivative, y prime, and I don't know its function at this point, but y prime intercept is 0.693. So I would have to look at my graph at this point or look at my table. Okay, how do the two graphs differ? Y prime is, we could say, is a vertical shrink of y equals 2 to the x. Okay, so we could think about it as 2 to the x times some scale factor that's less than 1 that's going to cause the y values to shrink. Okay, well, if the y-intercept of 2 to the x is at 1, and now the y-intercept of the derivative is at 0.693, then what would you say is the scale factor? Okay, so it looks like y prime might be some scale factor, some value that shrinks the 2 to the x graph. Okay, all right, well, again, if we go from 1 to 0.693, then I'm going to estimate that my derivative graph is actually 0.693 times 2 to the x. Okay, do you know the actual value, the well, I should say the accurate value, this is an estimate, this 0.693. Do you know a value that's truly accurate to represent this value? Any ideas? Let's take a look. If you play around in your calculator just a little bit, you might find out that 0.693 is actually an estimate of the natural log of 2. Okay, and that is actually the derivative of 2 to the x. Okay, here we're looking at the graph of 3 to the x. Okay, same exponential function form, right? So we're increasing. It's a little hard to draw, didn't do it very well. Okay. So same ideas though. Domain is all real numbers. Range is greater than 0. It's always concave up. All right. The derivative graph for this function, again, looks a lot like 3 to the x, but this time it's not below. It happens to land above. Okay, it's not going to cross there, but my graph's not drawn very well. So the 3 to the x graph, again, looks a lot like, the derivative looks a lot like 3 to the x, but this time the scale factor is not less than 1, it's greater than 1. Okay, so we've stretched those y values to become taller than what they used to be. Okay, by what scale factor? Well, looking at the table, it would appear that it's 1.0986. Okay, if you play around on your calculator here a little bit and check this out, the value of 1.0986 is actually equal to the natural log of 3. So the derivative of 3 to the x is the natural log of 3 times 3 to the x. All right, so we could say that the derivative of an exponential function is proportional to the original function. So that's what we're talking about. If we say f of x equals a to the x, we know where a is some real number. Actually, let me say that a is greater than 0. Okay, for exponential functions, a is greater than 0. We know that the derivative is proportional to the original function. So when we say proportional, we mean there's some kind of scale factor being multiplied by the original function. All right, and that, as we saw with 2 to the x, the scale factor was the natural log of 2. All right, I'm calling it a scale factor. It can also be called a constant of proportionality. So the constant of proportionality for f of x equals 2 to the x was the natural log of 2. That was less than 1. Right? And the constant of proportionality for f of x equals 3 to the x was greater than 1. That was the natural log of 3, which was greater than 1. Okay, so there must be some a value that lies between 2 and 3, such that the constant of proportionality must equal 1. So we're saying that for some f of x equals a to the x, its derivative is also a to the x, where the constant of proportionality is 1. Do you have any idea what value that might be? Okay, if you just think about our constants of proportionality for the previous two derivatives of 2 to the x and 3 to the x, well, the natural log of what number will equal 1? That would be the natural log of e is 1. So we can say that if f of x is equal to e to the x, f prime of x is equal to the natural log of e, or 1, times e to the x. You should check that out on your graphing calculator, looking at the table, and see if that holds true. Okay, you should find that the derivative of e to the x is itself. Okay, so just generalizing finally for derivatives of exponential functions. If f of x equals a to the x, then the derivative of f of x is the natural log of a times a to the x. Okay, special case is the e to the x, where its derivative is itself. All right, I'll see you in the next video.